All right, chemistry, this is your video lecture for part 2 of chapter 8. We are going to be dealing with both sections 2 and 3 together in this video. So we'll be going through section 2, the types of chemical reactions, building off of what we covered in section 1, and we'll finish up with section 3, the activity series of elements, which is fairly short, so I'm just going to tack it on to the end of this lecture. So at the end of this section, section 2, I want you to be able to define and give general equations for synthesis, decomposition, single displacement, and double displacement reactions. Now, those are several different types of reactions, and we're going to go over how to distinguish between those different types. Next, classify a reaction as synthesis, decomposition, single displacement, double displacement, or combustion, right? The same types of reactions with the addition of combustion right there. And so we want to be able to define those, give the general format of those, and then if I give you a real equation, a real reaction with actual chemicals, not just general, kind of that parent format, I give you a real reaction, I want you to be able to classify that as one of those 5 types of reactions. Next up, I want you to list 3 kinds of synthesis reactions and 6 kinds of decomposition reactions. Got a couple more. List 4 kinds of single displacement reactions and 3 kinds of double displacement reactions. And lastly, predict the products of simple reactions given the reactants. So as we get started, we're going to cover our 5 major types of reactions, and this might seem like a lot to bite off at once, but if you start with your definitions of each of these and your general equations for each of these, that's going to be your foundation for building the other details later. So there are several ways to classify chemical reactions. The classification scheme described in this section provides an introduction to 5 basic types of reactions: synthesis, decomposition, single displacement, double displacement, and combustion reactions. Now, before we get started with synthesis specifically, I want you to take a moment and look at those 5 types of reactions and realize that you understand what each of those words mean. And those are the names for the types of chemical reactions, the 5 basic types, because they are descriptive. Realize that you already have a clue of what you should be looking at just from the name. So let's start with synthesis, a bringing together of 2 entities, right? A bringing together. That's what synthesis is. To synthesize something doesn't just mean to make. That's kind of how we use it colloquially, but we're bringing 2 things together to make a new thing, right, when we synthesize something. So in a synthesis reaction, which is also known as a composition reaction, notice you know that word too, to compose, right, to put together, to create. 2 or more substances, right, synthesis, to bring together 2 things. 2 or more substances combine to form a new compound. And if we understand that as the definition, the name synthesis is very descriptive. That's exactly what the word synthesis means: to bring together 2 or more things to create a new single thing. So that's the definition. Now you need to be able to give the general equation. And this type of chemical reaction is represented by the following general equation, which is A plus X, right? Those are 2 generic chemicals. They're not actual chemicals. There's no element on the periodic table that's represented by A or X. But if we have 2 chemicals combining, right, chemically reacting to form a new thing, AX, right? It's not A by itself. It's not X by itself. It's A and X combined together into one thing. So it's 2 or more substances combining to form a new compound. Now, what we've represented here, A and X, they can be either elements, hydrogen, oxygen, or they can be compounds. They can be water, carbon dioxide, right? So don't fall into a rut where you think they have to be elements or only elements or only compounds. They can be either. But AX definitely is a compound, because even if A and X are elements, when they combine together, they form a compound. Oh, too fast. So this is a representation of a very, very common synthesis reaction, especially examples, knowing that you guys have taken biology and you're coming into this class after taking biology. Cellular respiration and photosynthesis, right? They're the reverse of one another. We talked about reverse reactions last lecture. We know that if we combine carbon dioxide and water with the help of a little bit of sunlight, we can create a sugar, glucose, and some spare oxygen. That's photosynthesis, is what happens inside plants. What we're doing here is we're taking two substances, carbon dioxide and water, and we're combining them to form something new. Here, the more important one is glucose. I guess I shouldn't say more important. Oxygen is also very important. But we're creating new compounds by combining old compounds. Now, we also have to know a few different types of synthesis reactions, and we're going to go over some very, very specifics. And so if, for example, on a quick write, I ask you to give a specific example of a type of synthesis reaction, this is your gold mine right here. One simple type of synthesis reaction is the combination of an element with oxygen to perform an oxide. Hopefully you remember from our unit on nomenclature that if something is bonded to oxygen, it's an oxide, right? Hydrogen peroxide, sulfur dioxide, carbon monoxide. It's that element combined with oxygen. It's called an oxide. Almost all metals will react with oxygen to form oxides because, as we'll see in section 3, oxygen is a fairly active thing. It wants to react. So an example of a metal reacting with oxygen to form an oxide is magnesium reacting with oxygen, right? To create magnesium oxide. Now, hopefully you notice that we have balanced this equation already. There has to be 2 magnesium atoms on the left side. There has to be 1 oxygen molecule. Notice 1 oxygen molecule has 2 oxygen atoms on the left side, so that when we have 2 magnesium oxide molecules, or I guess these are ionic compounds, so it'd be a formula unit, we have 2 magnesiums and 2 oxygens. Notice we've also included the states of phase. So all the elements of a correctly written and balanced chemical equation are here. So group 2 elements, of which magnesium is one, react in a very similar manner. They're going to react with oxygen to form the formula, a generic formula, MO, where M is any of those group 2 metals. Now, there are several other group 2 metals. Magnesium is just one of them. It's a very specific example. But if I give you another one, like on a quiz or a test or a quick write, calcium, for example, is another group 2 metal. It would combine in the formula MO. And so that specific example would be CaO, calcium oxide. Why do I only have 1 of each? Because group 2 elements form +2 cations, and so you only need 1 oxide to balance that out. So you have 1 group 2 atom and 1 oxygen. Group 1 elements, however, form +1 cations. So when they react with oxides, you have to have 2 of those group 1 metals. And so we have this general formula of M2O. Again, here M is not a specific element. It's just a generic representation of a metal. For example, lithium is a group 1 metal. And so if we're going to have lithium oxide, we're going to have 2 lithium atoms for every 1 oxide so that the charge is balanced. The group 1 and group 2 elements react similarly with sulfur, right? Because sulfur is right underneath oxygen on the periodic table. And remember, any elements that are in the same column as one another, the same group, they have similar chemical characteristics. And so if oxygen reacts this way, sulfur will probably react this way. And so we don't call it a oxide anymore. When you react with sulfur, we call it a sulfide. And it's going to have the same general formulas, an M2S or MS respectively, depending on whether or not that metal is from group 1 or group 2. And here are some examples. Rubidium. All right, rubidium reacting with sulfur. We have rubidium sulfide. Now, rubidium is group 1, so it's only going to form a +1 charge, so we need 2 of them for every 1 sulfur. So, Rb2S. Barium, however, group 2 forms a +2 cation, so we only need one barium for each sulfur. Barium sulfide, BaS. Nonmetals also undergo synthesis reactions with oxygen to form oxides. So not just metals, not just things on the left side. Things on the right side can also do that. We've already talked about one of the examples. Sulfur reacts with oxygen to form sulfur dioxide, according to this reaction here. Another example, hydrogen will react with oxygen to form dihydrogen monoxide, which you know as water. Again, note these balanced chemical equations that are very useful as examples if I ever ask you for one on some writing assignment. Most metals will react with group 17 elements, the halogens, to form either ionic or covalent compounds, either or. Group 1 metals will react with halogens to form ionic compounds. Obviously, they're metals, and they're group 1, so they have a +1 charge. The halogens are group 17, so they have a -1 charge, and so we'll only have one of each for a general formula of Mx, where M is the metal and X is the halogen. And here's an example of that. We have sodium reacting with chlorine to form sodium chloride. Now, please notice that chlorine is Cl2 because it's a diatomic molecule. To have a molecule of chlorine, it's not just one atom of chlorine, you have to have two atoms. Remember Brinkelhoff. That name is the list of diatomic molecules. Brinkelhoff. Another way to remember that is hydrogen. Hydrogen, oxygen, nitrogen, and all of the halogens, right? Anything that ends in gen, halogens, hydrogen, oxygen, nitrogen, they all exist as diatomic molecules. Group 2 elements will react with the halogens to form ionic compounds with the formula Mx2. Hopefully this is sounding a little bit repetitive now. We're just balancing charges here. Fluoride is going to have a -1 charge. Magnesium is going to have a +2 charge. So we're going to have 2 fluorides to balance out the 1 magnesium. And just as a note, this could be a little trick for you to use later on a quiz or a test or something. Fluorine is so reactive that it combines with almost every metal. And we use the term active. Okay, active. Active metals are highly reactive metals. If I say it's very, very active, it's the same thing as saying highly reactive. If I say highly reactive, it's the same thing as saying it is active. Oxides of active metals, right? So a metal that's very, very reactive and is bonded with an oxide will then react with water to produce metal hydroxides. Again, a metal hydroxide is just a hydroxide, an OH with a -1 charge, bonded with a metal. For example, if we have a calcium oxide, that's a pretty active metal that's already bonded with oxygen, so calcium oxide. If we react the calcium oxide with water, that water will rearrange itself to bond with the calcium and form calcium hydroxide. Now remember, calcium has a +2 charge, hydroxide has a -1 charge, and so we need 2 of the hydroxides to balance out the calcium. Many oxides of nonmetals in the upper right portion of the periodic table will react with water to produce oxyacids. Remember, an oxyacid is an acid that, in addition to hydrogen and whatever its base element is, also contains oxygen. So, for example, sulfur dioxide, if we react that with water, we can get a sulfuric acid, H2SO3, or that'd be sulfurous acid, I believe, sorry. Certain metal oxides and non-metal oxides will react with each other in a synthesis reaction to form salts, right? So we have calcium oxide and sulfur dioxide. Again, metal oxide. Calcium is a metal, so it's a metal oxide. And sulfur is a non-metal, so sulfur dioxide is a non-metal oxide. They can react with one another to form a salt. And a salt, is an ionic compound. Here, it's a calcium bonded with a sulfite. Moving on to decomposition reactions. This is the exact opposite of a composition reaction. Instead of composing, bringing together two things to make one new thing, we're taking that thing that we've already synthesized or has been synthesized at some point in the past, and we're decomposing it. We're breaking it apart. That's what the name means, to decompose, to break apart. So in a decomposition reaction, a single compound undergoes a reaction that produces two or more simpler substances. That's some weird formatting there. Or compounds, right? They don't have to break down into elements. They can still break down into just smaller compounds, but they're going to be more simple. You're going to see a smaller number of things turn into a larger number of things. And we'll see that when we look at that example down there. Decomposition reactions are the opposite of synthesis reaction. Instead of bringing things together, we're breaking things apart. And as we look at this general equation, AX decomposes to form A plus X. Think of, a model that you've built or that you've seen made up of Legos. When you buy that Lego set, it's a bunch of smaller Lego blocks, and you synthesize, you bring those things together in a very specific way, and you create one thing out of many. If we break that model down, if we decompose it, break it apart, we're taking that one model and breaking it into its constituent components, the individual Lego blocks, we're decomposing it. One example of decomposition that we want to be aware of is electrolysis. And again, look at the base roots in that word. Electro, as in electricity, and lysis, which is a breaking apart. Hopefully you remember that word from biology. Electrolysis is using electricity to break things apart, which makes sense because we're talking about decomposition reactions right now. We're breaking things apart. So the decomposition of a substance by an electric current is called electrolysis. If we take water, for example, and we'll try to show you a representation of this on the next slide, and run electrical current through it, that water will actually break up into hydrogen molecules and oxygen molecules, right? The components, the things that go into making water. Oxides of less active metals, which are located in the lower center of the periodic table, will decompose into their elements when they're heated, right? So we can decompose something by running an electric current through it. Not everything, but a lot of things. Water is the prime example. Or we can heat it. Instead of running electricity through it, we can heat it. And we represent the heating of something by the Greek symbol delta, and that little triangle right there. That always means with the addition of heat. Now, we're not being specific about how much heat we're adding here. We're just stating that we have to heat it. And so here's that representation of electrolysis. So if we have a sample of water and then we run electricity through it, we will see that our original sample, the water, right here, bottom right, water, we run that electricity through it, it's going to break down into hydrogen and oxygen, right? We're decomposing the water. We're breaking apart the water into more smaller, simpler things.
Electrolysis is the use of an electric current to cause an oxidation-reduction reaction. Electric current is the passage of electrons. Because oxidation is the loss of electrons and reduction is the gain of electrons, the passage of electric current through a solution causes these reactions. For example, when current is applied to water, the hydrogen in the water is reduced to elemental hydrogen, and the oxygen is oxidized to elemental oxygen. Because 2 moles of hydrogen are formed for every mole of oxygen, twice as much gas is formed in one tube as in the other. When the electricity is shut off, the reaction stops. Electrolysis is also used in electroplating.
Moving on with decomposition, we have to have some specific types of decomposition. We're talking about decomposition of metal carbonates, right? So any metal bonded to a carbonate, which is a polyatomic ion, any carbonate. We have the decomposition of any metal bonded to a hydroxide, and then the decomposition of any metal bonded to a chlorate, right? So you're going to need to be able to recognize the carbonate, the hydroxide, and the chlorate so that you can think to yourself, aha, when we see decomposition of a metal bonded to a metal carbonate, we're going to have the metal oxide, right? Calcium carbonate will decompose into calcium oxide and CO2. When we decompose a metal hydroxide, calcium is a metal, here's a hydroxide. If we heat that up, we get, again, the metal oxide, and what's left over, H's and O's, so that'll turn into water. And then here's chlorate, right? Hopefully you can recognize the chlorite, ClO3. It's got a -1 charge. That calcium will stay bonded to the chlorine, but ditch all of these oxygens, right? So we'll have a metal chloride and oxygen, free oxygen. We can, too fast. We can also decompose acids. Certain acids will decompose into nonmetal oxides and water. For example, carbonic acid. That's one of those things that is in a soda, right? That makes it all bubbly. The presence of carbon dioxide in water. Carbonic acid is unstable and decomposes readily at room temperature. That's why once you open that soda, it's going to become more and more and more flat, because it's going to decompose into carbon dioxide and water. That's why when you open that up, release the pressure. Sorry, when you open that soda up, release the pressure, little bubbles come out. That's carbon dioxide, and it's leaving behind water. So inside the soda is carbonic acid that will decompose once you release the pressure, and you are obviously at room temperature. That's why leaving a soda closed will keep it from going flat, and keeping it cold will keep it from going flat. Moving on to our next type of reaction, single displacement. Single displacement. You guys know what it means to be displaced. You're being moved, right? Someone's moving you out for something else. Now, how many things are being displaced? A single thing. One thing is being displaced. You'll see another term used interchangeably with this, replace, right? In some texts, and I actually believe in our text at points, the text refers to these reactions as single replacement reactions. I hope you know enough about the English language that you're not fooled, and that you understand that displacement is the same thing as replacement. If you're displacing something, you're getting something out of the way, you're moving it from where it was, and then you're going to replace that with something else. So many single displacement reactions take place in aqueous solution. And so those states of phase, it's not solid, it's not liquid, it's not gas. It has the letters AQ behind it. And in fact, now we'll talk about that later. Single displacement reactions can be represented by the following general equations. Notice we have an A reacting with a BX, right? So, A, B's, X's, Y's, they can all be elements. But when we have A reacting with a compound BX, whatever it is, it's just generic. If that A displaces the B, right, kicks it out, and then takes its place, right, and replaces the B. It displaces the B and then takes its place. That's called a single displacement reaction. Now, as a result, you would see now the A is bonded to the X and the B is by itself. That doesn't happen just with metals. Non-metals can also displace other non-metals, but please note that metals do not displace non-metals, and non-metals cannot displace metals. Like displaces like, and that's it, right? And so I have a second example, Y reacting with BX. The Y is not going to replace the B, the Y is going to replace the X. And so we would have Y displacing the X and replacing the X, forming a bond with B. Displacement of a metal in a compound by another metal. Aluminum is more active than lead. Remember, that just means that it's more reactive. It wants to do more. And so if we have a solution of lead nitrate, that PbNO3, there's got to be two nitrates to balance out that lead. If we introduce aluminum into that solution, right, it is a solution. Notice that that's AQ there. That state of phase is AQ. The aluminum will kick out the lead. It will displace the lead and take its place. It will replace the lead because aluminum is more active than lead. We can also displace the hydrogen in water, one hydrogen with a metal. Group 1 metals are the most active metals. They react vigorously with water, violently even to produce metal hydroxides. And so you guys know that water is H2O, 2 hydrogens, 1 oxygen. If we have a very, very active metal, for example, sodium is a very active metal. If we put that into water, the highly active nature of that sodium is going to displace one of the hydrogens and take its place. It's going to replace that hydrogen. Less active metals like iron, right, doesn't react anywhere close to the same level as sodium, will react with steam to form a metal oxide and hydrogen gas. So that iron is going to have a +2 charge or a +3 charge, and so it's going to have to kick out multiple hydrogens. So that's why we don't have an iron hydroxide. It's an iron oxide and all that free hydrogen. Now, notice that this is a less active iron. It still can react, it's just not going to react as strongly. You'll notice that we're still reacting with water, but now that we're talking about the less active metal, the example here being iron, we say it has to react with steam. It's still water, but it's steam. It's a different form. The reason that's important is because it has more energy in that state of phase. Water is cool, steam is hot. The water being in the gas phase means that it has enough kinetic energy to drive the reaction with iron. With sodium reacting with cold liquid water, the sodium is active enough on its own by itself. But iron, being less active, is not active enough to react on its own. It needs the extra kinetic energy that the steam brings, that hot water. It's steam, it's gaseous water. All of that kinetic energy is needed to also drive the reaction. We can also displace hydrogens in hydrogens and acids by metals. The more active metals, right, so like group 1 stuff, will react with certain acidic solutions like hydrochloric acid and some dilute sulfuric acid and replace that hydrogen in the acid. The reaction products are a metal compound, it's some sort of salt, and hydrogen gas. And so we have the example here, hydrochloric acid. That metal is going to displace the hydrogen and bond with the chlorine. Now we have to balance the equation. We have to understand that there have to be 2 chlorine atoms to bond with the magnesium. And so that magnesium will react with hydrochloric acid to form magnesium chloride and hydrogen gas. Halogens are very, very active, and so we need to go over what they're going to do. Fluorine is the single most active halogen. It's very, very active. It can replace any of the other halogens in their compounds. But remember, like only displaces like. So fluorine can only displace non-metals. So in group 17, each element can replace any element below it, but not any element above it. And we're talking about in the periodic table. So looking at your periodic table, we can see these example reactions. Chlorine reacting with potassium bromide. Chlorine is listed above bromine on the periodic table. It's physically above it. And so that means that chlorine is active enough to displace bromine and yield potassium chloride and free bromine. Fluorine is at the very top of that column, so it's certainly active enough to displace chlorine and form sodium fluoride and chlorine gas. But that third example there, we have bromine trying to react with potassium chloride. Bromine is not listed above chlorine. It is below it. That means it is not active enough to displace chlorine. So that means even if we mix these two things together, no reaction will occur. Now we're moving on to double displacement reactions. We're still talking about displacement. Things are being displaced and replaced. But instead of just one thing being displaced and one thing being replaced, we're up to double. So 2 things are being displaced and 2 things are being replaced. So in a double displacement reaction, the ions of 2 compounds exchange places in an aqueous solution to form 2 new compounds. One of the compounds formed is usually some sort of precipitate, some sort of insoluble gas that bubbles out of the solution, or a molecular compound, which would usually be water. The other compound is usually soluble and remains dissolved in solution. So let's get some examples up here so you can see what we're talking about. A double displacement reaction is represented by the following general equation. Now, pay attention to the differences between a single displacement reaction and a double displacement reaction that you can see pretty plainly here. Find the pattern. In a single displacement reaction, there was a compound reacting with a single element, right, or a single entity. Here, both things that are reacting are binary. There's AX, A with X, and BY, B with Y. These are all going to be different ions, right? They're in aqueous solution. AY and BX represent ionic or molecular compounds, right? The products. So here, A is displacing B and therefore replacing B to form AY. Well, A left X to bond with Y, and in doing so displaced B. So now B is available to bond with X because it's got nothing better to do. So we have to form BX. Two things have been displaced. Two things have been replaced. Double displacement. We covered what a precipitate is last lecture. The formation of a precipitate occurs when the cations of one reactant combine with the anions of another reactant to form an insoluble or only slightly soluble compound. That means that it won't stay in solution. It won't stay mixed in, and it has to fall out of solution. For example, if we react potassium iodide with lead nitrate, the resulting lead iodide is insoluble. And so it does not stay in solution, and it falls out of solution as a solid that will settle down to the bottom of the solution. But the potassium nitrate is soluble, and so it will stay in solution. Now, the reason that this precipitate forms is a result of the very, very strong attractive forces that exist between the lead cations and the iodide anions. It's because they're so strong they can't be torn apart to stay in solution. We can also do something very, very similar with a gas. Instead of forming a solid and falling to the bottom of the solution, we can form a gas, and we can bubble that gas out of solution. So if we react, for example, iron sulfide and some hydrochloric acid, the iron will displace the hydrogen in the acid to form iron chloride. That'll stay in solution. That one's fine, it'll stay in solution. But the resulting dihydrogen monosulfide, right, that's going to be a gas, and it's going to bubble away. It's not going to stay in solution. So we can form precipitate, we can form gas, or we can just form a molecular compound, which is usually water. Especially in this second example here, reacting an acid with a base, hydrochloric acid, sodium hydroxide, that's a base. The sodium will displace the hydrogen and bond with the chlorine to form sodium chloride, and that'll stay in solution. The displaced hydrogen will bond with the ditched hydroxide to form H2O, water in the liquid form.
When a colorless aqueous solution of ammonium sulfide is added to a colorless aqueous solution of cadmium nitrate, cadmium sulfide, a bright yellow precipitate forms. Let's take a look at the starting materials. In both cases, the reactant compounds dissolve in water because the electrical bonds between the ions are weak. When mixed together, the ammonium, sulfide, cadmium, and nitrate ions come in contact. As a result, cadmium sulfide forms. The bonds between cadmium and sulfide ions are strong, and they begin to form large clumps of neutral crystalline lattices. We see this as a brilliant yellow precipitate that falls out of solution. The remaining ammonium ions and nitrate ions remain in solution.
And our last reaction type is combustion. In a combustion reaction, a substance combines with oxygen. Always have to be oxygen present. You've probably heard, an old axiomatic phrase, something like oxygen is required to burn, but doesn't burn itself. Here's where we're going to be able to describe the truth of that. When a substance reacts with oxygen, it will release a large amount of energy in the form of light and heat. So if we combust hydrogen, meaning we react hydrogen with oxygen, we actually form water, right? When we react hydrogen gas and oxygen gas, we'll form water. But a lot of light and heat is released in the process, right? A kind of explosion, one might say. A lot of light, a lot of heat. We don't just combust hydrogen, we can combust hydrocarbons like propane, right? C3H8 in the gas form. If we react that with oxygen, it'll burn, it'll combust. And as a result, we'll have carbon dioxide and water. So these are very, very common examples. Notice that as we go through some more examples, notice the consistency in the types of products.
Methane, like many fossil fuels, can react with oxygen in a combustion reaction, releasing heat and forming carbon dioxide and water. The amount of oxygen available is very important for this reaction. When the supply of oxygen is limited, carbon monoxide, a poisonous gas, is formed. At very low oxygen levels, soot, or tiny pieces of carbon, are formed.
And this chart right here, this graphic right here is absolutely fantastic. Please pay attention to this. Please have this out while you're trying to conceptualize of these 5 different reaction types and trying to make heads or tails of them and see the patterns. See the patterns. Combustion, something is combining with oxygen, right? And it's going to be exothermic. It's going to release, give out energy in the form of light or heat. When we synthesize things, we're bringing together 2 substances to make something new. And you might not be able to tell the difference between the synthesis and decomposition right now just by looking at the equation, but let me give you a hint. For synthesis, we have simple things. They're smaller things combining to form more complex things. And here's an easy way to check. Notice for that synthesis reaction, we have 6 carbon dioxides and 6 waters that are coming together. That's 12 things. 12 things, 6 plus 6. That's 12 things coming together. And how many things do we have as a result? Well, there's 1 glucose, which is a pretty big complex thing, and 6 oxygens. That's only 7 things. So we have 12 things mixing together to form 7. We went from a large number of things to a smaller number of things. Now let's see what that looks like for decomposition. We have that larger thing, the glucose, with its reacting with its 6 oxygens. That's 7 things breaking down into now 12 things. Right? So use that as a little trick when you're trying to look through your quiz questions and test questions. Then we have single displacement and double displacement. Things are being displaced and then replaced. The difference being, is there only 1 atom taking the place of another, or are there 2 atoms trading places? Okay, so keep this graphic out. It is absolutely critical. And here also, right after the graphic, I've included a kind of a dichotomous key, how I want you to go about figuring out whether or not you're looking at combustion reaction, single displacement, double displacement, synthesis, or decomposition, right? And it only has 5 steps. So read through those and you'll see how you can go through and knock these things out. All right, let's get on to section 3. There are only 2 objectives here because section 3 is very easy. It's very, very simple. So this is probably not going to take very long at all. Explain the significance of an activity series and use an activity series to predict whether or not a given reaction will occur and what its products will be. So you guys already know, we just talked about it a few minutes ago. The ability of an element to react is referred to as the element's activity. The more readily an element reacts with other substances, it's said to have greater activity. So an activity series is a list of elements organized according to the ease with which the elements can undergo certain chemical reactions. Do you remember we looked at an example of a reaction where we were trying to mix together bromine and a chloride, something that was bonded with chloride, and it said no reaction because bromine, we said, was not active enough to displace the chlorine. Now, the activity series is a list that allows us to make that call for any reaction that we look at. So in order, the order in which the elements are listed is usually determined by single displacement reactions, right? That's just kind of a factoidal thing. That's how the activity series is generated. You don't necessarily all the time just look at the periodic table and know what is more active than what. It's done experimentally, right? Scientists have already done it. The most active element is going to be placed at the top. That means that it can replace all of the elements listed below it in any single displacement reaction. Activity series are used to help predict whether or not certain chemical reactions will occur. And so if I ask you to predict whether or not a particular reaction will occur and then predict its products, you're going to be using an activity series. And yes, you will have to just use a list that I will provide. You don't have to memorize these or know how to read the periodic table to find them, because you're going to have a list that looks just like this, right? So we have activity of metals and we have activity of halogens. Remember, non-metals can only displace non-metals, right? So here we only have 4 to choose from: fluorine, chlorine, bromine, and iodine. They're only going to be displacing each other. They will not displace a metal. Now the activity series of metals is a lot longer. You'll probably be doing a lot more problems using the metals. And so lithium on this list is the most active metal. It will displace everything below it. Rubidium is the second most active metal on this list. It will displace everything on this list except for lithium, and on and on and on.
An activity series is a categorization of elements based on their reactivity. For example, alkali and heavier alkaline earth metals react readily with cold water, oxygen, and acids. Lighter alkaline earth metals, aluminum, and some transition metals will not react with cold water, but will still react readily with steam, oxygen, and acids. Some heavier metals will react with acids and oxygen, but are unreactive to any sort of water. Other heavier metals will react with oxygen, but are inert to acids and water. A few transition metals, such as gold and silver, are very unreactive.
All right, chemistry, that will do it for sections 2 and 3. I will see you next period.